Hello, welcome to the Domino Data Lab Tools for Multicore Data Science in R and Python webinar. I'm Eduardo Ariño de la Rubia, Chief Data Scientist at Domino Data Lab. As Chief Data Scientist at Domino Data Lab, I work with our customers to help them establish best practices, take advantage of cutting-edge tools, and create impact using data and machine learning. I have a background in computer science and conflict resolution, building software and analytical solutions for global multinational logistics, manufacturing, and education companies. Domino is a data science platform and system of record that lets you use the statistical programming languages you already know and love with the data wherever it is that it lies, using the IDs and tools that you've already mastered. On top of that, we overlay compute automation, environment management, version control, sharing and discussion, and publishing and deployment. This allows you to have faster experimentation, collaborate better, have better reproducibility and auditing, integrate models into the business faster using REST APIs and the like, and this gives you more time for data science. For this webinar on scalable multi-core data science, our compute automation feature was incredibly useful. I was able to spawn jobs on very large hardware with just the click of a button. I had up to 128 cores and 2 terabytes of RAM available to me. Compute automation really made this webinar possible. In this webinar, we're going to cover 4 topics: what, why, and when to leverage multiple cores, tools for multi-core data science in R, tools for multi-core data science in Python, and finally, some language-agnostic tools for multi-core data science. So now, let's cover the what, why, and when of multi-core data science. There's a lot of talk about parallel processing and distributed computing. Let's cut through the hype and discuss when it's really going to be useful. Parallel processing is using your computer's capabilities to do many things at once and get done sooner. Unlike humans, who almost always degrade in the quality of their results when they multitask, computers can do many things at once without degrading in quality. A computer can multitask as many tasks as it has cores with fundamentally zero degradation. Multi-core computing refers to using multiple processors on a single physical machine or image. This leverages the locality of reference and the speed of modern memory and buses. The capacity of machines has grown significantly in recent years. However, distributed computing paradigms such as Hadoop, Spark, and traditional HPC approaches such as MPI require often significant overhead and infrastructure. These leverage processors across many different computers through the network. Referencing 1K of data in main memory takes 100 nanoseconds. Sending 1K of data over even a 1 gigabyte network takes 10,000 nanoseconds, 100 times the latency. Distributed computing should only be used when a single machine cannot be found with the required capacity. Why do we care about parallel architectures and multiprocessing? Because time is precious. The data science process involves increasingly demanding processing. From training ever larger models to feature engineering to hyperparameter tuning, oftentimes processing power is the bottleneck to experimentation and ideation. Performance is a competitive advantage. The data science process is complex and often involves many stakeholders. Parallel or multi-core processing won't be applicable for all of the stages. Multi-core or parallel processing will help primarily in these 4 stages. Collecting data, or reading and writing, this is getting data in and out of your data science pipeline. It can take an inordinate amount of time, and parallel processing can significantly speed it up. Transforming or manipulating data. The work of a data scientist involves taking data from its current form and transforming it into some other form often. This can be incredibly time-consuming without parallelism. Model training. Building models is an intensively compute-intensive task, oftentimes requiring billions of mathematical operations even for the simplest model. Sometimes, but not always, these operations can be parallelized. And finally, validating and understanding your model. Industry standard best practices for validating a model often include processor-intensive tasks like cross-validation and resampling. These tasks can be parallelized and get massive speedups. As a warning, whenever you're going to parallelize your tasks, make sure to profile and match your resources. You have a limited amount of CPU, I/O, both disk and network. Make sure to actually measure your performance. Saturating a resource will create a bottleneck, and parallelization cannot get you around those bottlenecks. Let's explore some tools for multi-core R. The R ecosystem provides a number of tools for parallel processing. In this section, I investigate some of them and provide you with some real-world performance benchmarks. First, we're going to cover the venerable Parallel package. Parallel was first included in R 2.14 and provides drop-in parallel replacements for most of the functionality of apply, with integrated handling of random number generation. Parallelism can be done in computation at many different levels. This package is principally concerned with coarse-grained parallelization. The crucial point is that these chunks of computation are unrelated and do not need to communicate with each other in any way. Here we have some example code that I wrote using the Parallel package. The key note here is note MCLapply as a drop-in replacement for lapply, where all I have to do is set the number of cores. Here, I'm going through and writing out a number of files, 500, in parallel, using the reader package and the write CSV function. I then do the same thing, only backwards. I read those files back, using MCLapply again, getting all the results in here, and using read CSV. I do this for a number of cores so that I can actually plot the performance. Though R does not provide a native way to leverage writing multiple CSVs in parallel, if you have a list full of data frames to write, you can use the MCLapply from Parallel. And as you can note, you actually get a pretty nice speed up, right on around 32 cores. After that, it seems that there's really diminishing returns, but it really can cut down your time for writing vast numbers of CSV files. Similarly, although R does not provide a native way to leverage multicore CSV reading, if you do have a directory full of CSV files, you can use Parallel and MCLapply to read them all at once. This, however, is not a clear-cut performance gain. Going up to 8 cores worked really well in my benchmark, and I was able to get a pretty linear speed up. But once I went over 8 cores, I actually got slower and slower performance. This is probably due to a bottleneck created in the I/O subsystem. So, if you are going to do parallel CSV reading, I do suggest doing a little bit of benchmarking, but right around 8 cores seems to be a sweet spot for my use case. These use cases were for writing many CSV files. What if you want to write out one CSV file as fast as possible? Datatable is a venerable and powerful package written primarily by Matt Dally. It is a high-performance implementation of R's data frame with an enhanced syntax. Even Matt Dally himself cautions against using Datatable in multicore environments. However, in November of 2016, Datatable got a fully parallelized version of fwrite, its CSV writing function. It allows R to write out data with a significant speedup. This is Matt Dal's answer on Stack Overflow to the question of using Datatable in parallel computing. He states that the mantra is rprof, 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 and I agree. It's important to profile whenever it is that you're doing multicore. So here's the code that I wrote to profile how parallel fwrite from Datatable works in different multi-core situations. Here I'm iterating through the number of cores, and I'm just doing an fwrite to temp, just a junk CSV file, n threads equals n cores. This is a pretty big data frame. It ends up being something along the lines of it's the diamonds data set, but I end up like you'll notice, I create a big data variable where I rbind it 100 times over, and then I cbind it 10 times over. So we end up with something along the lines of 500,000 rows and 500 columns. As you can see, with fwrite's numthreads parameter, I do get a pretty good performance speedup, although it is diminishing returns. Something interesting happened here around 8 cores. I should probably investigate that further, but overall what I see as a trend is that you do get better performance with the more cores. I will say, however, that going from 64 to 128 cores is a significant jump in cores and only a small change in performance. The Parallel package is a low-level building block, replacing R's apply with MCLapply. A slightly higher level construct is the for each loop. The for each package replaces the traditional R for each loop with a parallel version. The main reason for using the for each package is that it supports parallel execution. That is, it can execute each iteration on a number of processors or cores on your computer, or if you have it configured as multiple nodes on a cluster in a distributed system. If each operation takes over a minute, so each loop iteration takes over a minute, and you want to execute it hundreds of times, you have hundreds of things to iterate over, the overall runtime can take hours. By using the for each package, that operation can be executed on parallel in hundreds of processors, or cores, reducing the total execution time back down to minutes. For my sample for each code, I simply created a number of samples of the iris dataset, and then I used the for each loop, and I said, let's go through these number of trials, and I did 100,000 trials, and then I just sample from the dataset, and I create a GLM, predicting something from the iris dataset. all of these iterations happen in parallel. These bootstraps can be completely independent from each other. And the for each package delivers. I get a significant speed up. We see the same pattern that we've seen historically, is that there's a point of diminishing returns, although that really depends on what you need in your business. It's possible that for you, this delta is really, really meaningful, but it's possible that for you, this delta is the most meaningful. However, it's good to note that it seems that the parallel for each loop does scale pretty well. The Carrot package, highlighted in Kjell Johnson's and Max Kuhn's applied predictive modeling, short for classification and regression training, is a set of functions that attempt to streamline the process for creating predictive models. The package contains tools for data splitting, pre-processing, feature selection, model tuning using resampling, variable importance estimation, as well as much other functionality. There are many different modeling functions in R. Some have different syntax for model training and/or prediction. The APIs for example, GLMNet and random forests are different. The package started off as a way to provide a uniform interface for the functions themselves, as a way to standardize common tasks, such as parameter tuning and variable importance. However, the addition of parallelism turned it into a high-performance model-building environment. In my Carrot example code, I once again take advantage of the diamonds dataset. Here, I'm again iterating through just the number of processors that I want to use, and calling Carrot's train function, its gateway to all of the machine learning models in R, to just train to try to regress price on all the other data for the diamonds dataset. I'm doing inline pre-processing, center and scaling, and Carrot knows how to handle that properly, making sure to handle all of the centering and scaling inside of the resamples to make sure that I'm not overfitting. Carrot handles all of that for me and fully parallelizes all of these resamples. Carrot delivers. It does all of that hyperparameter tuning, figuring out exactly what all my hyperparameters need to be in the resamples, and it spreads it really nicely across multiple cores. We do see that even at 128 cores, we are getting small performance speedups. And the last R package that I will cover is Hadley-Wickham's multi-dplyr. Multi-dplyr is a backend for dplyr that partitions the data frame across multiple cores. You tell multi-dplyr how to split up the data with partition, and then the data stays on each node until you explicitly retrieve it with collect. This minimizes the amount of time spent moving data around and maximizes parallel performance. Due to the overhead associated with communicating between nodes, you won't expect to see much performance improvement on basic dplyr verbs with less than around 10 million observations. However, you'll see improvements much faster if you're doing more complex operations with do. Multi-dplyr is a joy to work with if you're used to dplyr's pipeline syntax. So, in here, we set the number of cores to use again. In this case, we were not able to use 127 cores in the X1. It seems that R had some difficulty dealing with quite that many cores. We create a cluster with that number of cores. We partition our data onto each one of those cores. And then we're, by destination, creating a generative additive model. So this is what we were talking about. It's a more complex operation than a standard dplyr operation. On a dataset with 330,000 rows sharded across many cores building these models, we do get a significant performance speedup, really topping out at around 16 cores. Although again, on your particular data and your particular environment, you'd want a profile. We do see that again after 16 cores at 32 and 64 cores, the performance begins to degrade, and we were not able to test 128 cores. However, this is a significant speed up, from 6 to 2. It may be worth it in your particular models to see if multi-dplyr is the right thing for you, especially if you find yourself using the do verb. In conclusion, we've covered a number of packages for R. The parallel package as a basic building block to building parallel constructs, data table to write out data quickly for collection by other systems using fwrite, the for each package to make it easy to iterate over data in parallel simply, Carrot to build and validate models using advantage of a unified interface and multiple cores, and lastly, multi-dplyr, munge data, build pipelines, and enhance your exploratory analysis leveraging many cores. Now we begin our session on tools for multi-core Python. The Python ecosystem provides a number of tools for parallel processing. In this section, I investigate some of them and provide you real-world performance benchmarks. Getting data into your pipeline can be very time-consuming. Paratext is a C++ library to read text files in parallel on multi-core machines. The alpha release includes a CSV reader and Python bindings. The library itself has no dependencies other than the standard library. Paratext is the fastest CSV reading library in the world, according to our benchmarks. Paratext and Pandas achieved a significant improvement in performance leveraging multiple cores. We were able to get a pretty significant speed up right around 16 cores, and then after that performance began to degrade. This might have to do with the size of our CSV or the number of columns. In your scenario, go ahead and test and profile yourself, but Paratext does provide significant multi-core performance improvement. JobLib is a set of tools to provide lightweight pipelining in Python. In particular, JobLib offers 1. Transparent disk caching of the output values and lazy reevaluation, a nice memoized pattern. 2. Easy, simple, parallel computing. 3. Logging and tracing of the execution, which can be really nice for debugging multiprocessing or multi-core code. JobLib is optimized to be fast and robust, in particular on large data, and has specific optimizations for NumPy arrays. In this JobLib sample code, I'm creating a large number of line segments, then a smaller number of segments to test to see if they cross, and I have a function to check to see if one line segment contains another. Then I benchmark it by going through each number of cores and then saying, just creating a parallel construct, setting the number of jobs available, saying that I want to check the paths for the test segment, for each text segment in the number of segments that I wanted to check to see if a line contained another. This automatically parallelizes, and here we see the results. For this kind of work, where all of the work can be done in parallel with no internode communication, JobLib is incredibly hard to beat. Here we see basically speed up all the way through 128 cores. Again, diminishing returns at the tail, but still speed ups at every step. JobLib provides incredible multi-core performance for the right class of problem. And finally, for Python, I will talk about scikit-learn. Scikit-learn, if you don't already know about it, is a free software machine learning library for the Python programming language. It features classification, regression, clustering algorithms, from support vector machines and random forests to gradient boosting, k-means, and dbScan. It is designed to interoperate with the Python numerical and scientific libraries, NumPy and SciPy. Scikit-learn provides very easy access to leverage large multi-core servers by simply using the njobs parameter. This works for many models. It also works for grid searching, cross-validation, etc. Scikit-learn is an incredibly well thought out, powerful machine learning library. For the sample code for scikit-learn, I leveraged some pre-existing work from Szilárd Pafka's machine learning benchmark. Here I'm going to just train a scikit-learn random forest classifier. I'm doing some data cleanup here and creating some categories. And the same thing I've done previously, I'm using the time package to actually get snapshots. I'm iterating over the number of cores that I want to try. And simply, I'm training a random forest classifier with 500 trees, setting the njobs parameter and calling fit on that model object. The performance gain is pretty undeniable. Scikit-learn gives me performance speedups throughout all of the processors. It's important to note that although this particular experiment is simply training a random forest classifier, scikit-learn pipelines can leverage parallelism in many, many different ways. Like I said earlier, from cross-validation all the way to model training and grid search, scikit-learn really leverages multi-core processing. If you're a Python data scientist and you're not leveraging large multi-core computers and your training and your scikit-learn pipelines take a while, you're literally leaving just time on the table. For Python, we covered these 3 packages to let you really speed up your data science leveraging multiple cores. Paratext, which gives you fast access to CSV reading, leveraging multiple cores, getting you significant speedups. JobLib, a powerful building block for distributing embarrassingly parallel work on many cores. And scikit-learn, one of the world's most powerful machine learning libraries for Python. It makes leveraging multiple cores as easy as just setting the njobs parameter. And in this last section, I want to cover some language-agnostic tools for multi-core data science. The data science ecosystem provides a number of tools for parallel processing. In this section, I will investigate 2 of them and provide you some real-world performance benchmarks. First, I'm going to cover the H2O machine learning library. H2O provides some of the best machine learning algorithms on the planet. They have implementations of GLMs, GBMs, random forests, deep learning, and a number of other algorithms. The H2O library is pretty language agnostic. It can be called from both Python and R, and it is written in Java. H2O can leverage multicore computers, and through simple configuration provides nearly linear speedup in those configurations. In my sample H2O code, I'm training a random forest on the airline dataset. The only configuration that needs to be done in order to leverage multiple cores using H2O is when you initialize the H2O server, and this happens to be R code, call the number of threads with the number of cores you wish to leverage. From that, everything will leverage multiple cores. It's surprising, but H2O's import file functionality itself is a parallel CSV reader. Training a random forest is easy. I just pass the parameters, tell the number of trees. The parallelism is already implicit because of the way it was initialized. And the only thing I had to do was initialize and shut down the H2O server between each loop iteration to set the number of cores available. H2O's library performed rather admirably. It was able to get nearly speedups all the way up to 64 cores. At 128 cores, there was a little bit of a degradation in performance, but I was able to get pretty significant speedups for training this random forest on 100,000 rows on 500 trees all the way through 64 cores. And finally, I will cover XGBoost, the secret of the Kaggle masters. XGBoost is an optimized, distributed, graded boosting library designed to be highly efficient, flexible, and portable. It implements machine learning algorithms under the gradient boosting framework. XGBoost provides a parallel tree boosting, known as GBDT or GBM, that solves many data science problems in a fast and accurate way. The same code runs on many distributed environments, Hadoop, SGE, and MPI, as well as multi-core processing on single images. It can solve problems beyond billions of rows and examples. In the sample code, we see that leveraging multiple cores is really straightforward in XGBoost. All that you have to do, after you've created your sparse model matrix with the data that you wanted and you're ready to actually train the number of cores, you literally just have to call it with nthread equals cores. This does everything that you need to automatically parallelize the building of the GBM across multiple cores on your system. XGBoost performed pretty well. I was able to get performance improvements through multi-core and parallel processing through right around 32 cores. After that, I saw performance degradation at 64 cores and significant performance degradation at 128 cores. I'm not real sure what caused this significant performance degradation, but I will be researching it and updating the webinar if I find out more later. In this section, I covered two language-agnostic tools for parallel multi-core data science. The H2O library, which provides world-class algorithms with great multi-core performance, and XGBoost, powerful gradient boosting with multi-core capabilities in a single parameter. Both these libraries can be accessed from R, from Python, and from many other languages. In conclusion, multi-core tools are awesome and can provide significant speedup. Is there any big lessons we can learn out of all of this? I hope you take away at least these three things. There are many parallel uses in data science. You can use it from the data science pipeline, from writing CSV files, reading CSV files, to model tuning. Parallel processing is useful to the data scientists. There are many libraries that make it real easy. These are high-level APIs. They're no longer just message passing or building blocks to take advantage of multiple cores. They work at the layer of abstraction that you as a data scientist want to work. And that it's really supported in a lot of languages. R and Python both have tools that make taking advantage of multi-core processing intuitive for data scientists. You're not having to build weird distributed algorithms or worry about making sure that memory contention doesn't happen across multiple threads. You could work really at the layer that you want, in the language that you want, and take advantage of architectures from 2 cores to 127 cores. Perhaps the most important point is that as a data scientist, your time is precious. Model training, model validation, data munging, these are really taking increasingly demanding amounts of processor. As a data scientist, you have to provide value to the business quickly. You have to react, you have to be able to be inventive, and you have to be creative. Parallel processing makes it easy for you to try out more ideas, try out more experiments, and come up with more innovative solutions. Performance and speed is a competitive advantage.